Swayam Prabha. Digital India. Educated India.
Welcome back. In lecture 40, we will talk about life cycle assessment. The concepts that we will cover is the ISO 14040-2006 LCA framework. Within that, we will talk about goal and scope definition, goal and scope definition in the context of solid waste management, life cycle inventory analysis, landfills as carbon sink, life cycle impact assessment, life cycle interpretation, and finally, we will show you some examples. So, we have earlier we have talked about evaluation between different waste disposal alternatives or different technologies for that matters. Now we can do it in a very broad way using the cost of those particular options and all. But if we want to do a detailed analysis of two technologies that are involved or two processes that are involved, it's better to use the LCA framework. And as we have discussed earlier, there is environmental impact assessment and then there is the LCA framework. And in case of LCA, as you remember, LCA looks into the entire gamut, the entire extent of the product's life cycle starting from cradle to grave. And that is how it gives us opportunity to compare the product not only at the final, as a final option, that is at the disposal or like during the final choice, but during every stages of that particular product, starting from when it was mined to how it was processed, then how that particular product, what sort of processes went into that. All these things, if I compare, then at every stages there are emissions, there are environmental impacts, and if we compare all of this and together we can assign that total environmental impact of that product is this, we may find that some obvious choices of technology that which we feel that this is a better technology actually turns out to be not so good in the long run. So that if I consider the entire life cycle of that particular product. So that is why LCA framework, LCA analysis is more detailed and it gives us opportunity to really investigate a product or a process, right? So this ISO 14040-2006 LCA framework, so this is developed by the International Standards Organization. So it provides a standardized framework for conducting LCA. So we can always, because if there are no standard frameworks, then anybody can compare any two products in whatever way they feel is more suitable or more or based on availability of data, they can adopt their own methodology. But if that is done, then there is no standardized method, or in some cases certain things will show some results. In another study, the same two items will show different results, right? Which one is better or which one is more friendly to the environment and so on. So it's better to create a standardized framework following which everybody can do this LCA analysis. So that is where ISO has provided this framework. 14040-2006. 2006 is the year and in which this framework was updated. So that's why the year is given, but the framework is ISO 14040 framework. So environmental impacts of a product, process or service are investigated throughout its life cycle in LCA. And so how we do that? So to do that, we follow certain steps. In this particular image, you can see the steps which are listed in the framework for life cycle assessment as given in the ISO guidelines. What are the steps? The first step is goal and scope definition. The second step is life cycle inventory analysis. The third step is life cycle impact assessment, and finally interpretation. As you can see that there is all these stages, the arrows goes both ways. That means when I define the goal and scope of my work, based on that, we have to create life cycle inventory. But based on the inventory, based on data availability, based on many other things, we may modify our goal and scope. Similarly, for life cycle inventory, we can determine its impact. That means for different products, different components of the products, different inputs for the products and processes, of course. For each of this, there are different impacts that are generated. Now, impacts also may, may help, because certain impacts are, when we compare across different products, some impacts are same, right? Exactly same impact is happening for both products. So in that case, I may say that, okay, these are the components which are same between the two products, so I can ignore those parts, right? So accordingly, I have to modify the inventory as well. So all these things, that means this is not a fixed procedure, step by step in sequence. We can always modify it in each direction, and then we can finally come to a position where we can say that this is the final LCA framework for, or final comparison between two products. And all these stages, there is a stage called interpretation. Interpretation is done at the beginning and also at the end. That means once all these results are coming in terms of the products and processes for each product or each process, we have to see their impacts and so on. So then we have to interpret these impacts or interpret what it means as per the goal and scope of our work, and accordingly we have to take a decision. So this interpretation stage is actually happens at each of these intermediate stages as well as at the final stage. So this LCA is used for, usually once you do the interpretation, then based on the interpretation we can determine so how a product, which processes should be adopted for a product development, which processes are more environmental friendly, and how we can improve the existing processes of a product, right? So that is what are existing processes that are adopted. Maybe if I consider landfilling and incineration, so each has got different processes, different products involved in it. So in which stages we can make improvement. Then it can help us in strategic planning to take decisions beforehand. Public policy making. So because we are evaluating two products, we can say that these are the environmental impacts of this particular process or product, and that actually helps us in making public policy. And finally, it helps us to do marketing and also in other aspects. So to do all this, first we have to compile an inventory of inputs and outputs to this product, process or service, or otherwise known as inventory analysis. So inventory of inputs and outputs for each product, process and service has to be first listed. That means input means what things goes into making of that product or that process, and what are the outputs from that product or process. So all this needs to be first computed. The impact assessment phase determines the potential impacts of each of this input and output, and then determines which the overall impact and output for this particular impact for this particular product. So each input that goes into making a product or a process, each input results in some pollution, some emission, some effect, right? Now sometimes two inputs together goes into a process and then there is an emission. So I have to assign certain amount of the emission to each of this input. So these are the challenges that are there, but overall we have to understand that there are certain inputs goes into the process, there are certain outputs comes out, and some of these outputs are harmful from the environment. So finally the results are interpreted as per the objectives of the study. So interpretation is not like there is a straightforward yes and no answer. We have to compare the product at different stages of its life cycle, see what kind of effects is happening, which are the common effects, which are the uncommon effects. Then we have to determine as per our objectives of study what should be this product which should be chosen, or which part of or process of that particular product has to be changed or modified to make it more environmentally sustainable. So the first step is goal and scope definition, and goal and scope is defined as per the intended application, and it can be revised midway. So I have already told you that we can revise the goal as per the inputs or as per subsequent stages. We can modify the goal and the scope. So goal and scope gives us the reason for conducting the study and its audience for whom we are creating this particular study. So LCA study, if I am creating it for a decision maker, it may have a different goal compared to if I am creating it for a particular industry, it will have a different goal based on what are the targets of this particular intended audiences. One may look at reduction of the overall cost, provided some constraints on emissions are there, whereas the other may look into the reduction of overall environmental and other kinds of cost for a particular process or a product. Then this also helps us to give comparative assertions for public between the products. The scope within a particular product or a process, the functions are defined. These are performance characteristics for reference or comparison. So each product can have different functions or different characteristics. So we are comparing those for reference or comparison between the two products. And functional units are thus defined and measurable, right? So functions are performance characteristics. That means whenever we are comparing different products, we break it into different functions, and those are the ones which can be compared. I will give you some examples later. So system boundary, once this basic functions are defined or performance characteristics are defined based on which we will compare the two products, then we have to define the system boundary. Now, the system boundary could mean the different processes and the level of detail of the study. That means when I am comparing two products, if I go into details of the study, we can reach to such minor details which may be too difficult for the audience to understand. Or it could be at such a level where that both of the studies are more or less same, right? So that means suppose one is incineration, one is landfill. In that case, I may ignore certain processes, or like for example transport of the waste to each of the sites. Maybe the certain aspects of transportation, like what sort of vehicle was used and all this, we can ignore that because that is more or less same in both the vehicles. But the distance of transportation, that I will consider. So when I am considering overall waste management or comparison between incineration and landfill, it involves transportation cost, it involves the vehicle of transportation and all these things, right? But I can assume that the vehicle is same in both cases, and I can ignore the entire aspects related with vehicles for this study. So that is how we define the system boundary. Some life cycle stages, processes, inputs or output is deleted if it does not alter the results and conclusions significantly. So that is what I was saying, that some of the stages of processes or some of the processes, some of the inputs outputs, if there is the same among all the different options that we are comparing, then we can even ignore them. The other thing is beginning and ending of a process. That is, for example, in case of waste, the beginning of the comparison of landfill and incineration should start from the waste itself. But the waste didn't start as a waste. It was some other material. That material was created using some other processes. It came from it used certain raw materials. So how far ahead we will go? So where is the beginning? So raw materials and intermediate products which are there for each of this process or product that we are evaluating. So this raw materials and intermediate products which comes in between, some of them could be considered, some of them can be ignored. And similarly for ending of the process, for example, once the waste is discarded, in that case, that some of this waste could be transferred to a recycling facility where it is converted into another product. So should I end the life or end my analysis when I am processing this product? There is some amount of energy spent, some cost spent at that level, or should I again consider the next product which is prepared out of this product and again follow it up, right? So this boundaries needs to be considered. And the transformation during the processes, right? So beginning and ending of the process and the transformation of the process, what we should consider, what should be the boundaries, that is determined. Then cutoff criteria for input-output allocation. Not all input-output has to be considered. things which are common can be ignored, things which we are not comparing, that can be ignored. Like for example, CO2 emission happens at different stages of, for making a particular product or a process, but maybe we can say that CO2 coming from biotic resources we will not consider. Why? Because we assume that whatever is a biotic source, that could be, that means a plant, we can again plant that, you can again grow another plant, and when it grows, when a new plant grows, it will take the carbon from atmosphere, CO2 from atmosphere, and the carbon will be held within the plant. Then when you decompose, or when when this plant gets decomposed eventually, then again the carbon is released into the atmosphere. So I can decide that I will not consider this process, because I will assume that for whatever plants I am destroying, I will also put in similar amount of plants. But we are not, if we are not doing that, then that has to be considered. So that is what this input output allocation, this cutoff criteria has to be considered. Then else this then impact assessment methodology and types of impacts that we are considering is also needs to be determined. That means what sort of impacts we will consider. There are different impacts that is caused by a certain product, but not all may be considered, because it is beyond our goal and scope, or that is beyond the need for the current scope of study. Then overall interpretation is also aligned with goal and scope. Data and data quality, requirements, assumption, limitations, these are determined, and type of critical review and format of report which is required finally, that is also required. So just to give you an idea, over here I have taken this from this study, where you can see the elementary composition of constituents of waste, and this is used as input in the comparison of incineration and landfill. Now, for example, you can see that if I break a particular product, or if I break a, if I take solid waste management, if I take paper, or if I take organic waste, or if I take plastic waste, each of them could be broken into its primary elementary constituents, right? So these are some of the elementary constituents that we can consider. Now it is our job to determine which we will consider and which we will not, right? For example, this TS is the total solid, that is weight after evaporating moisture. HHV is the higher heating value. This is value of energy content, including energy in stream produced in combustion. C fossil is carbon of fossil origin. C dot bio is carbon of biological origin. C lignin is carbon in stable carbohydrates. C cellulose is carbon in semi-stable carbohydrates. Then coming to protein, carbon in protein form. H is hydrogen, except hydrogen in water. O is oxygen. VOC is volatile organic compounds. Then PCB is polychlorinated biphenyls. Then you take all the different aluminum, potassium, calcium, paper, lead, cadmium, mercury. So these are the primary constituents of any product, right? So some of these constituents would be there in a product, in other products it would be not. So now it is our job to determine which of these inputs we will consider. That should be defined in the goal and scope definition. That because we are only looking at this sort of environmental impacts, then maybe some of this we can ignore, right? For example, if I take food waste, newspaper, corrugated board, mixed cardboard, polyethylene, polypropylene, polystyrene, polyethylene terephthalate, this is PET bottles, polyvinyl chloride, this is PVC. So this kind of material is there in any kind of municipal waste stream. Now, if I break it up for each of those primary, elemental constituents, you can see the quantity of each one of them in food waste, newspaper, corrugated cardboard, mixed cardboard, and so on. So, like these are the items which are not there in PE, right? So that is polyethylene. Whereas this kind of there are other things, like for example over here, like this kind of metal are available in all the materials. So you can see that these are some common items. So these are specific to this particular items that we consider. So we have to determine what sort of input we should consider and what sort of we shouldn't. So this is a very, very detailed analysis of taking what inputs goes into making of a product and a process, because until unless I know the inputs, I will not be able to determine what would be the environmental impact of this particular input that goes into the process. Now, coming in the context of solid waste management, when we have defined goal and scope, we have defined it in general terms, but if I take the context of solid waste management, I will make things more simpler. For example, I have to consider the upstream and downstream system boundaries. That's part of goal and scope. Now, in municipal solid waste management, input is solid waste which originates from households and other generators. So, in that case, the upstream system boundary could be parts of the system or process which are identical in all compared systems can be ignored. So, part of the system process which are identical in all compared systems can be ignored. So, if I am considering incineration and landfill, both are dealing with waste. So, everything beyond, before this item becomes a waste, that can be ignored because these are all common between incineration and landfill. So, I am only concerned about once it becomes waste, then what happens in incineration, or then what are the inputs, and then each of this input will lead to some amount of emission or some amount of environmental impact that we have to decide for each of these particular, all these different aspects, right? So, as we are discussing that all parts which are identical in all compared systems can be ignored. So, we are only concerned with the part where the solid waste has been disposed, the waste has been disposed by the households and all, and then we start comparing them, right? Similarly, downstream system boundary, materials or energy can be recycled into new products. Recycled products and products replaced by this are not followed to their disposal normally. So, normally we don't do that, but sometimes we do that. That means, if I have an aluminum can, after recycling it becomes again aluminum can, right? So, should I consider that aluminum can as well, or till it becomes is finally disposed? So, what should be the end of my comparison, right? So, when I am comparing between different processes, that means different processes to recycle aluminum can, I shouldn't look into what happens in the subsequent stages, right? So, I end over at the end of this first recycling procedure. So, that is how we create this upstream and downstream boundaries. So, these are very, very subjective. It depends on the goal and scope of the study. It depends on what is my reason why I am doing the study and so on, why I need to compare these two processes and so on. So, based on that, we have to determine this. So, system boundaries can be also time related and also geographical boundaries. Why? Because some of the impacts are also based on geographical boundaries. That means, if there is some pollution happening, that may spread into many bigger, larger geographical areas. Should I consider everything? Or it could be spread over a long time. For example, in landfill and incineration, particularly in these two things, the effect of time is significant. Why? Because in landfill, impacts are spread over a long time. That means, in landfill, the waste products remain inside and then gradually those breaks down. For example, materials such as plastic will keep on being there for the next 10,000 years maybe, whereas certain metals and all keeps on gradually leaching out. That means, leachate keeps on coming out of this particular material from metals and all. So, this will also be a slow process, but it is not as long as for plastic, but it will still go on for a long time. Whereas, in case of incineration, that is immediate. Whatever energy you are putting in to incinerate, and then some amount of emissions coming out. So, we can know what emissions are happening within a very short period of time. So, we need to create these time boundaries. That means, when I am comparing incineration and landfill, I may consider a longer time boundary for landfill, but we have to determine how much is long, right? So, these time boundaries are also important. So, these are the different kinds of boundaries we need to create before we start any sort of evaluation. Then, open loop recycling. Now, we earlier talked about that once a product is recycled, we may ignore it, right? So, we don't need to look into downstream. But there are some cases where it has to be considered. So, why? That means, environmental interventions can be allocated between two products and only one is considered. So, that means, whenever some impact happens, the final impact, which product should I consider? Should I consider it at the first product or the recycled product, and so on? So if that second product could be recycled further downstream, right? So eventually the environmental impact has to be divided amongst these three products, or it should be assigned to only one product, or considering both products within the system boundary. So we considered both the products within the system boundary. We considered the recycling system, what process has gone into, what energy, what material has got into the recycling process, the primary material used in both products, and materials disposed from both products are considered. So the disposal can happen at the end of life of the second product, or it could happen all throughout the life of that product, depending on what sort of product it is. Suppose it's a tire, so it keeps on losing material all throughout its life, and then once it is retreaded and it is used for the second time, again it will keep losing material. So it could be looked into for the entire life of that particular product over multiple uses over its life, right? Recycled material, but along with that, suppose a product is recycled. A recycled material replaces virgin material with similar functions. That means when I'm using a product, when I'm recycling it, what is happening is I'm not taking new material from the environment or new raw material. So that's reduction of virgin material. So that also needs to be considered. So there is more cost, transportation energy, or certain process cost that goes into recycling. But at the same time, we are avoiding transportation of virgin material, avoiding taking of this new material. So that is obviously a benefit. So the entire thing needs to be considered. Thus, downstream processes are considered identical and disregarded in some cases. Sometimes it can be considered, sometimes it can be disregarded, right? So that is what we have to decide. So open loop recycling is another aspect that we should be careful about. Then multi-input allocation. In case several products are inputs to a process, allocation of environmental interventions for each product becomes difficult. So for making one process or making one product, there is a certain process, but it requires many products to go into that. So as I have shown you that there are, we can break a product into many components. Now once that is there, which product component is leading to which pollution, that is very, very difficult. So this is something which is very, very problematic. So multi-input allocation is done considering physical, chemical or biological relationships. So that means we have to study the chemical, biological and other processes in detail to understand what is being changed into what and what are the emissions resulting from which aspect, and accordingly do this allocation of emission to a certain input. Now, why this is important? Because there may be another product where I can change that input and I can improve the process significantly, because this input is creating that pollution. So if I change only that one single input or one single constitutional element, then the product would be significantly better. So that's why we have to say which input leads to which output or which pollution that they are generating or which emission they are generating. So life cycle inventory analysis is the data collection and the calculation phase, and where relevant inputs are linked to the different outputs. And so to do that, we have to identify the product systems and the processes that are involved, raw materials and energy extracted from the environment. So what this is known as the input, and all inputs return to the environment as emissions to air, water and land, and processes flow charts and data on each process needs to be collected. So we really need to look into scientific literature, government and industry sources to see that what are the processes, what sort of inputs they take, what is the output. We need to understand the overall process in detail to do this kind of input-output allocation, right? Or to create this kind of inventories. Boundaries are set for the product system under consideration. Boundaries in terms of the environment, from other product systems, and for processes not taken into account. So what process we should not consider, those are immediately let out. So the aggregated data results in an inventory table and economic inputs and outputs converted to environmental inputs, resources and outputs, emissions. So I will show you some examples. So these are some of the different input related categories and the output related categories. So in life cycle inventory analysis, we actually determine what are the inputs and outputs, and we also in goal and scope we determine which inputs we should consider and which output we should consider. So inputs are abiotic resources, biotic resources and land. Abiotic resources could be again of three kinds: deposits, funds and flows. What are deposits? Deposits are resources which cannot be renewed within a limited time, such as fossil fuel and maybe some mineral ores. That means once we use it, they cannot be reused again, or we cannot recover those materials again. Funds are resources which are renewable but can be depleted. That means wood, fish, if you keep on taking it from the environment, you will run out of it. But if I plant a tree, instead of once I cut a tree, I also plant a tree, then it will be, we are renewing that particular resource. Flows are resources which cannot be depleted, like wind, solar radiation and all these things. This cannot be depleted at all. So so this cannot be depleted, but they can be deflected. That means they can, by changing wind patterns and all, we can deflect, or we can make sure some people are getting it, other people are not getting it, but usually they cannot be depleted. So anyway, deposits, funds and flows are there, and some of these could be abiotic resources, but for biotic resources, then most of these are funds. That means woods, fish, these are mostly biotic resources, whereas abiotic resources could be both deposits, funds and flows. So, and land is of course another input. So, these three are the inputs, and then we have to break these inputs, each of these input, into constitutional elements to determine the detailed composition of this particular inputs. Then again, how much detail you will go into, that's up to you. So, it depends on what processes are involved, it depends on which interventions you are looking at. So, if you are looking at incineration, but you want to improve the process, so in that case you have to go into those detailed compositions, and then each process and which inputs goes into each process, you have to look into that in detail. But if I am doing a study in broad, comparing incineration and landfill, considering the overall environmental impacts, then probably I don't look into that much detail. So what are the output related categories, or what are the impacts? It could be global warming, depletion of stratospheric ozone, human toxicological impacts, ecotoxicological impacts, photooxidant formations, acidification, eutrophication, odor, noise, radiation, casualties and so on. So these are the different impacts that we can consider for each of this particular product. So I was talking about this. Landfills could be modeled as carbon sinks. Carbon flows into landfill when in case of landfill, what happens? We are putting mixed waste into the landfill. We can put mixed waste into landfill, right? Even though it's not suggested, we should only put inert and other kinds of waste, but we can put mixed waste into the landfill. In that case, what happens? A lot of carbon gets trapped inside the landfill. So in that case, should I consider that? Biotic carbon from renewable sources such as plants and all is usually not considered. Why? Because as I told you that it is, as soon as I plant another tree, it will take carbon from the environment and it will again grow. So even though I am putting it in the landfill site, it is not considered, right? Because we are again taking that carbon from the atmosphere. Then because once you put in the landfill site, decomposition will happen, and this CO2 will be released into this carbon will convert into CO2, CH4, it will get released into the atmosphere, and the plant is taking back this carbon from the atmosphere. So it's a cyclic process, so we can disregard it, right? Whereas for non-biotic carbon, such as from fossil fuels, these are considered. So cellulose, in case of cellulose, when I compare incineration and landfill, 100% of carbon emitted as CO2. Since it is biotic emission, these are disregarded. So in incineration, when I burn cellulose, in that again it's an organic matter, right? So when I burn it, CO2 will be released, but we don't consider it as an impact. Whereas in case of landfill, 70% is emitted quickly, and the other, the rest takes a long time beyond my system boundary. So within maybe 5-10 years, 70% is emitted, so it's my system boundary, but after that I'm not even capturing the gas and all, so it's beyond my scope of work, so I'm not considering it within system boundary. So 70% is released as CO2 and CH4 after decomposition. So in that case, CO2 is disregarded because it is coming from biotic sources and all, but CH4 is not disregarded because CH4 is a harmful global warming gas. it is almost 19 to 20 times more harmful than CO2, so we will consider that. So it is how we evaluate or what we consider, what we not consider, that up to how we frame our problem. Rest 30% of carbon is trapped in the landfill. So what we should consider, what we should know, what we should not, that depends on many assumptions. Depending on system boundaries, depending on goal and scope, we have to finalize this. So when I compare incineration and landfill, what I should consider, what I should not, these are the things that we have to be careful about. Then comes the life cycle impact assessment phase. So this is the phase where we actually look into its effect on the environment. So we have the inventory table. From there we have create these different kinds of impacts. These are the gases CO2, CH4, CFC. These are coming out. This leads to global warming. So this is the impact. Similarly, SO2, NO2, NH4 that comes out as output from based on the processes that input goes through. Then this leads to acidification. NOx, NH4P, this leads to eutrophication. Overall, so these are the different effects that is created. Each of these effects may be of different causes, different nature of harm. This could be again added up to create an environmental index to create an overall effect on the environment. So each of these effect categories could be again combined using some procedure so that we get an overall index, so that we can tell that which product or which process leads to what sort of impact in the, and accordingly we can take a decision. So LCIA, Life Cycle Impact Assessment, is an exploration and evaluation of the magnitude and significance of the potential environmental impacts of a product system. This is different from EIA, and this is a relative approach based on a functional unit. So EIA is absolute values, but done at the as a impact of a particular project or a particular product, whereas this is a relative approach similar to the ranking procedures that we have discussed earlier, and it is based on the different functional units that we are considering as per goal and scope. It could include everything starting from cradle to grave, or it may include only a certain part of it. LCI includes selection of impact categories. These are the different impact categories, category indicators and characterization models. Assignment of LCI results to the assignment of LCI results to selected impact categories, which is known as classification. So this is classification. Quantification of contributions to the chosen impacts from the product system. This is characterization. So this is classification, and this is classification, and this is characterization. Normalization, then we have to normalize the results, relates to the magnitude of the impacts in different categories to reference values. So we can take a reference category and then accordingly we can normalize the entire result. We grouping includes sorting and possibly ranking of the indicators, which is creating the most highest problem. Weighting is aggregating results across impact categories, resulting in a single result. So we can give weights to each of these values, each of these effects, characterization effects, and then that will lead to this environmental index. So similar to what we have done, there is impact, there is what sort of impact it is creating and the weight of that particular aspect to create an overall environmental index. So this is what life cycle impact assessment is all about. Finally comes the life cycle interpretation phase. As you can see that we have goal and scope, inventory analysis, impact assessment. All of these stages is interpreted. All of this has to be interpreted, and we have to identify the significant issues, and the evaluation is done and it is checked for completeness. We check the sensitivity and consistency, right? And also some other checks are there. And finally, conclusion, limitations and recommendations are done based on the interpretation that we do. So results are interpreted as per the goals and scope of the study. So as per our goals, we will do the interpretation. This includes assessment and sensitivity check for inputs and outputs and methodological choices. So for each input, if I change the input by this, how much would be the effect? That is the sensitivity analysis. And methodological choices, what methodology leads to what sort of effect, that we can evaluate. Uncertainty of the results, sometimes the results that we are predicting, these are uncertain. So instead of giving single values, we can give ranges or probability distributions for some effects right? What should the probability of that happening? So we can give that as well. Then the different checks are completeness, which ensures availability of relevant and complete information and data required to do this kind of checks. So completeness check of the data. Sensitivity check is ensure reliability of the final results and conclusions, because we are checking what affects what, and we are checking that multiple times. Effect of uncertainties in the data allocation methods or calculation of contributions. This is actually taken care in this particular step. Consistency check is assumptions, methods, and data are consistent with the goal and scope. That consistency check also has to be done. So coming to some examples, I can compare between different processes, or we can compare a single process, a single product, or a single option, and we can look into the different processes, and we can see that how are the impacts happening and which stages, and then we can suggest certain changes for certain changes as well using LC analysis. For example, over here we are discussing newspaper recycling system using paper, of course. So paper production requires thermomechanical pulp production. Some amount of electricity and heat is given to do this process, and this could be augmented, or we can reduce virgin material use by using recycled pulp production. But recycled pulp production requires first collection of waste paper, then transport and reloading of this paper to the maybe the processing center or that pulp production center. The pulp production process requires additives, electricity, heat, and it also generates some amount of non-treatable waste which has to be taken to the landfill site. So there is, energy use, some impact for all of these stages. Eventually the paper is produced, but in the meantime, what is avoided? Avoided virgin paper production. If I would have produced this paper, then we would have used heat, electricity. So these are all avoided because we are not using this. Then avoided thermomechanical products, avoided cleaning, avoided transport, avoided wood extraction, transport of it, cleaning of that wood, conversion into pulp, and so on. And similarly avoided heat production from forest residues and all, and so on. So you can see that because we are using recycled material, we are avoiding lot of processes in the because we are using recycled material. But recycling also takes up certain energy, certain electricity, certain heat, and so on. So I have to compare both of them to see if the additions in terms of environmental impacts because of these processes is more than the avoided environmental impacts because we are using recycled material. So if this is less compared to the avoided impacts, definitely this is a better process. So we will adopt that. So sometimes we can say that we should recycle, but sometimes it may happen that if I recycle, the overall impact is actually higher compared to if we are not recycling. So in that case, it's better not to recycle. So these kind of decisions could be taken when you do detailed LCA analysis. Coming to another example, this is PET bottles recycling. This is one form of plastic recycling. So here also transport, first of all, we collect this waste PET bottles, we bale them, we know that is we press them, make them into blocks. That requires electricity, that requires certain strappings and all to make them into bales. Finally, these are transported. That also we will spend energy on fuel. We will spend fuel and all, so that will lead to certain environmental impacts and all. So eventually, PET recycling happens. We require that electricity, natural gas, nitrogen, polymers, and all these things for PET recycling. But in the meantime, we have avoided virgin PET production, avoided electricity, avoided certain resources, avoided this waste that is also generated from PET production. So we are looking into in detail all the different processes which are connected with this PET production, including transportation of waste generated in the processes, and also the emissions and all that is happening, and eventually we are taking a decision if this is suitable or not. Okay. Finally, coming to the composting system, composting leads to fertilizer production. So, once we are this is the food waste that is generated, it is transported and that requires energy, and some amount of non-treated waste is also there in food waste that goes into the landfill side. The rest goes into the composting facility. Then it generates some amount of residue which also needs to be transported to the uh, uh, which also needs to be, some of it generates some amount of sludge and some amount of other waste material which goes into the landfill, right? So it has to be transported. Similarly, the rest is transported and used as fertilizer in the fields, right? Spreading of the composting residue. Now, because we are doing composting, we avoid creation of artificial fertilizer. And because we are avoiding artificial fertilizer creation, then avoided production of artificial fertilizer, avoided spreading of artificial fertilizer. So these are the two savings that we have done. Now, we can again go into detail of this particular process, and we can find out what sort of energy, what sort of environmental impact is there for artificial fertilizer production. So we have to look into the entire process in detail. So if I just look at composting, the cost of composting, cost of transporting it, then it will feel that composting will lead to a lot of cost compared to just the cost of fertilizer. Whereas if I consider that because of composting we are not producing fertilizer, and all production of fertilizer have got many processes inbuilt in that, and we are avoiding each of these processes, emissions from this process, then probably composting is a very desirable way to treat this organic waste that is originating in urban areas. So this is how we should analyze each of this aspect in much more details compared to what we have learned earlier. Then we can take a really proper call on which should be done or not, which process should be adopted or not. So these are some of the references that you can study. And to conclude, LC offers a more comprehensive way to evaluate the environmental impacts of a product, process, or a service. And standardized frameworks also ensure consistency of the analysis and interpretations.